This is session D3, spin 1/2 particles and their spin states. Last session, D2, was on two-state systems. We'll be leveraging all of that material today. This lecture may be longer than usual, but I want to cover a lot of material, especially a lot of experiments that prove spin 1/2 states, but I don't want to divide the lecture in two and have people start in the middle. It's not a lot of new material, but spin 1/2 is strange, so we will look at a lot of cases, a lot of experiments to understand it. And you'll get the hang of this, and so at some point you'll be able to speed up the lecture because you get it. Here's the approach we're going to take. In lecture D1, we learned that the Stern-Gerlach magnetic experiment causes a beam of neutral silver atoms to split into two beams based on the intrinsic spin angular momentum of silver's single unpaired electron. With the magnetic field in the z direction, the component of the electron's intrinsic spin angular momentum, the z component, is plus or minus h bar over 2. This is characteristic of a spin 1/2 particle, which the electron is. But the z direction was not special to the silver atoms leaving the oven. There was nothing in the oven that oriented the atoms magnetically. We defined abstract SGZ and SGX machines, and we're going to use those in this lecture. This lecture will only cover spin 1/2 particles. It's not applicable to spin 1 photons. We said earlier that spin 1 photon polarization is a two-state system, but it is not a spin 1/2 system. We'll cover photons in a future lecture. I think the typical approach to teaching about spin 1/2 particles is to learn the results of several different Stern-Gerlach experiments and incrementally get to a point where you are then told or you develop the general spin state for a spin 1/2 particle. You will cover angular momentum, you will cover rotations, you will get to that point of a general spin state for spin 1/2 particles. Then you go back and see that the general spin state is consistent with all those Stern-Gerlach experiments. Sometimes, in fact often, you will have learned how to do a change of basis, rotations and transformations of state vectors and operators in order to get to that point. I don't want to cover change of basis in this introductory series, so I'm going to use a different approach. I want to leverage all the material on two-state systems, lecture D2, without repeating the material, and I want to be clear to identify in this lecture what is unique for spin 1/2 particles, being the most important instance of a two-state system. If you have not watched lecture D2, you should go back and do it now because we will leverage all of those results here. I will give you the general spin 1/2 state from the outset and tell you how each Stern-Gerlach machine operates on the input state to produce its two output states. We'll go through a series of SG machine experiments and see how the states and operators produce the experimental results. Then we'll cover some final material. But we will not do rotations and the algebra of angular momentum operators in order to prove the general spin 1/2 state. I'm just going to give it to you. For the remainder of this lecture, we'll be considering a single spin 1/2 particle that is input to a particular experiment, Stern-Gerlach experiment, which will have 1, 2, or more outputs. Feel free to think of this particle as an electron or a proton or a neutron. If it's important to you to think back to the magnets inside the SG machine, feel free to consider the particle to be a single neutral silver atom. But I hope that you will try to think more abstractly and consider the particle to be an electron or a generic spin 1/2 particle. If possible, don't think back to the magnets, just think of the abstract behavior of an SG machine. In a future lecture, we'll consider how spin combines when we have two particles. That is interesting, it's important, but it has to wait. We have to learn the behavior of a single particle first. We're going to be dealing with probabilities, and if you're okay with thinking about probability associated with a single particle and a single event, that is going to be how I present it. Even though, probabilities can only be verified or tested by using large ensembles of identically prepared states and systems. But the experimental physicists have already done these experiments. We want to use their probability results and verify against our probability results for our state vectors to be sure that we understand spin 1/2 state vectors. This is a possible time to take a break. Now we have to start with basis vectors. As for any two-state system, we must start with a choice of a pair of independent, non-overlapping physical basis states. Two physical basis states selected for the particular physics of that system. The choice of basis states is not unique. For a spin 1/2 particle, we can choose any direction in three-dimensional physical space for the first basis state, but then the second basis state must be the opposite direction in space, so antiparallel or 180 degrees from one another. Opposite spatial directions result in non-overlapping physical basis states for a spin 1/2 particle. This is the first essential aspect of spin 1/2 particles. We can see how opposite spatial directions are consistent with the Stern-Gerlach experiment. One spot corresponded to the z component of spin being parallel to the magnetic field, and the other spot corresponded to the z component of spin being antiparallel to the magnetic field. So we use this understanding to identify the spatial orientation of the two basis states. The opposite spatial directions of two physical basis states for a spin 1/2 particle make spin 1/2 unique from a different spin, such as a spin 1 photon, where two spatial directions 90 degrees apart are non-overlapping for a photon. We can choose any direction in space for the first basis state, but we choose this to be the direction of the magnetic field of our first SG machine, as defined in lecture D1, and we call this the plus Z direction, or simply Z. Following will be our normalized basis vectors 1, or Z plus, or Z up, and 2, Z minus, or Z down, for spin 1/2 particles for the remainder of this lecture. Those are the basis vectors for state vectors and for operators matrices. We're not going to cover change of basis in this lecture series. We will use the ket form and its column vector representation in our basis, and also the dual bra form and its row vector representation in our basis. So the ket Z plus is the same as the ket 1 or E1 or E1, and in our basis the appropriate column vector is 1, 0. This is the Z plus direction. Now, Z minus is the second basis state, ket Z minus, ket 2, ket E sub 2, or E sub 2, and it is represented as 0, 1 in our basis. Those are the ket forms. We know how to take the bra forms. Bra Z plus is bra 1 or bra E sub 1, and it is the row vector 1, 0. And bra Z minus is bra 2 or bra E2, and it is the row vector 0, 1. Some classes and books elect to use up and down, either the words or arrows, up arrow and down arrow, where I will use plus and minus in this lecture. They mean the same thing. I just find it easier to type plus and minus and to speak plus and minus rather than up and down. These two basis states are orthonormal with the following inner products. The inner product of Z plus with itself is 1, the inner product of Z minus with itself is 1, the inner product of Z plus with Z minus is 0. They are orthonormal. The two basis vectors have unit norm or length. When the particle is in the state of that basis vector, the particle is wholly in that state, probability of 1. The two basis vectors are physically non-overlapping. There is none of one basis vector in the other. They have zero projection, one to the other. This is a matter of physics for our choice of basis vectors for a spin 1/2 particle. For the remainder of this lecture, all vectors and matrices will be representations relative to our predetermined choice of basis vectors. We're not going to cover change of basis. So we will have one basis set for the entire lecture. I will say basis. I always implicitly mean orthonormal basis. So if I just say basis, it is the orthonormal basis. This is a possible time to take a break. Spin 1/2 state space. The state space for a spin 1/2 particle is a two-dimensional, complex-valued, abstract vector space. Now that's true of all two-state systems. Now, this abstract vector space is not physical space, even though the basis vectors have directions, opposite directions in physical space. You must not think of the abstract vector space as being physical space. It's not. And this will be difficult at first to remember that states are vectors in an abstract space. They are not position vectors or direction vectors in real space. If you remember that the two basis vectors for spin 1/2 have opposite directions in physical space, that might help you to remember that those state vectors are definitely not spatial vectors in a physical two-dimensional plane. Let a general spin 1/2 state be represented for our chosen basis by ket V and bra V being ket V is the column vector with components V sub 1 and V sub 2, complex numbers in general. And so in this column vector representation, we mean v sub 1 times ket z plus, which is our first basis vector, plus v sub 2 times ket z minus, which is our second basis vector. Now the bra form, bra v, is a row vector, v sub 1 complex conjugate and v sub 2 complex conjugate, which is equal to, or means, v sub 1 conjugate bra z plus v sub 2 conjugate bra z minus, where bra z plus and bra z minus were our basis vectors, bra 1 and bra 2. In general, the components of a state vector could have dimensions in units such as angular momentum. However, for this lecture, state vectors will be dimensionless to allow us always to determine a state's probability. We think of the Stern-Gerlach experiment as the beam of silver atoms being operated on by the spin component operators SZ being h bar over 2 times sigma sub z, the Pauli matrix sigma z. Well, obviously here, h bar has dimensions of angular momentum, so the z component of intrinsic spin angular momentum has dimensions of angular momentum. In order to keep state vectors dimensionless so that we can determine probabilities, we will see that we will use the dimensionless Pauli matrix sigma z as the beam splitting operator rather than SC in this lecture. We know we're dealing with spin 1/2 particles. We know the magnitude of their z component of intrinsic spin angular momentum is always going to be h bar over 2 to spin 1/2 particle. So we just don't need to carry this extra information with each state vector, and we really want to use the state vectors to tell us probability of finding the particle at one output port or the second output port of an SG machine. Now the state ket v is not necessarily normalized. It might be normalized in some places and in other places not normalized. And this is intentional. The probability of the particle being in the state ket v, or equivalently of the state being occupied by the particle, if and when we do a measurement or a detection, is the square of its norm, so it's norm squared. So the probability for a particle being in state ket v is the inner product of v with itself, which is v sub 1 conjugate v sub 1 plus v sub 2 conjugate v sub 2, and that equals the square of the magnitude of v sub 1 plus the square of the magnitude of v sub 2, remembering they're complex numbers in general. But their magnitude is a real number, and the square of it is a real non-negative number, so the probability is always a non-negative real number. This is a possible time to take a break. Spin 1/2 state vector for a direction in physical space. In lecture D2 on two-state systems, we found that for all two-state systems, we can choose to write the general normalized state vector. I'm going to reuse v here, but in this case it's normalized. We can choose to write that as cosine of an angle alpha for the first component and sine of angle alpha times e to the minus beta, where alpha and beta are angles. They need not have any physical spatial significance whatsoever for a general two-state system. But note the need for complex numbers to fully represent state vectors of the complex vector space. The complex exponential e to the I beta, in general, that does not go away, and that does affect results. it gives rise to interference, quantum interference. So we need complex numbers. This follows from our analysis of two-state systems generally, not uniquely from spin 1/2, but spin 1/2 inherits that need for complex numbers. Differing from a general two-state system, for a spin 1/2 particle, we have the following two properties which might be surprising, certainly interesting. For every normalized state vector in the abstract vector space, we can identify a unique direction in real physical space. And the second property, for every direction in real physical space, we can identify a unique normalized state vector in the abstract vector space. So for spin 1/2 particles, there's a one-to-one correspondence between a normalized state vector and a unique direction in real physical space. So we have a one-to-one relationship between spin 1/2 normalized state vectors and directions in real physical space. Now for particles of spin 1, like a photon, or higher, I believe the first property may be true, at least for non-zero rest mass, but the second property is not true. But we're dealing with spin 1/2 particles, so they are both true. Now before we chose our basis vectors, we had set our Cartesian right-handed coordinate axes. And from these, we can use ordinary spherical coordinates. We can identify a vector direction in real space as being polar angle theta from the plus z-axis and azimuthal angle phi from the plus x-axis. Now I said there was a one-to-one correspondence, and in fact there's a simple representation. For a spin 1/2 particle with spin state component, positive eigenvalues eigenvector, vector direction, n vector, in real physical space. So its angles are theta and phi with respect to the z-axis and x-axis, which are going to be constant throughout this lecture. The angles won't be, but the axes will be. That spin state's normalized state vector. So for n vector in pointing in real space, the abstract spin state's normalized abstract state vector, the representation in our basis, this is going to be subject to arbitrary overall phase. We'll talk about that later. Ket n vector plus, so pointing in the direction, the positive direction of the n vector. The components of the spin state vector are cosine theta over 2 for the first component, sine theta over 2 e to the I phi for the second component. And so in our earlier two-state system, we had cosine alpha and sine alpha. Those get replaced by theta over 2. Alpha was not a physical direction for an arbitrary two-state system, but for spin 1/2, we do have a definite direction, theta, in our spin state. And phi is the same as beta. So now we have a ket for a direction in space whose components depend only on the direction in space, the angles theta and phi. We can go from ket form to bra form. We end up with the row vector, cosine theta over 2, sine theta over 2, e to the minus I phi. We're not going to prove that this is the correct representation of a state in space. To do that, normally a class will give you change of basis and rotation, and you'll deal with angular momentum and generators of rotation, and we don't want to do all that work. I tell you this is the state, and what we're going to do is we're going to conduct 9 SG experiments throughout this lecture and see what these states will, what experimental results we would get from the SG experiments, SG machine experiments. And I tell you that in every case that agrees with the experimental results. So you can believe me that this is the state. We have not proven it mathematically, and we're not going to, but we are going to go through experiments that will always agree with experimental results, and they're all based on this representation of the spin 1/2 state vector. This is a possible time to take a break. Now, we define n minus as being in the opposite direction, so if we had the opposite direction of vector, it would be in its plus direction. We can do a little trigonometry, we can change the overall phase, we get the following results, which you can just take from me. That n in the minus direction is the column vector sine theta over 2 minus cosine theta over 2 e to the I phi, and the bra form is the row vector sine theta over 2 minus cosine theta over 2 e to the minus I phi. Now, you can verify that those two states, n plus and n minus, they're orthonormal. And I encourage you to go check that for yourself. That these two state vectors for opposite spatial directions are orthogonal, that's partial evidence that it is a correct mapping to spatial directions. It's necessary but not sufficient that those two representations be orthonormal. Now, overall phase of either state vector's representation does not change this orthonormality, and if that's not obvious to you, you could check it by adding an overall phase to one or the other and verifying orthonormality. These two state vectors, they have unit norm, unit length, so when the particle is in that state of that state vector, the particle is wholly in that state, probability of 1. These two state vectors are physically non-overlapping. There's none of one state vector in the other, the zero projection. It's a matter of physics for spin 1/2 particle spin states. Now, I already said this wording once before. I said it once before in terms of z plus and z minus, which were our basis vectors. Now I'm saying it in terms of n plus and n minus. And z plus and z minus are just an instance, one instance of n. For every direction in real physical space, we've identified that direction's normalized spin 1/2 state vector in the abstract vector space. Now, if we were given the general normalized spin 1/2 state vector in this form, the two-state form, cosine alpha, sine alpha e to the I beta, where we didn't know at first what directions in space there would be, the only direction in space that they can be for it to be a spin 1/2 state vector is theta is 2 alpha and phi is beta. For every normalized spin 1/2 state vector in the abstract vector space, we've identified that spin state's unique direction in real physical space. This is a possible time to take a break. spin 1/2 state vectors for x, y, and z in physical space. We determine the spin 1/2 state vectors for the x, y, and z directions in real physical space simply by substituting the appropriate values for theta and phi in our general form with n vector. As always for this lecture, these are representations in our chosen basis, z plus z minus, and overall phase is going to be arbitrary. Now for the x direction plus x direction, that is polar angle theta of pi over 2, relative to the z-axis, and azimuthal angle phi of 0. If we just substitute those in to our earlier formulas, we get that ket x plus is 1 over square root of 2 times column vector 1, 1 in our basis, which was the z basis. And we can turn that into bra form, 1 over square root of 2 row vector 1, 1. The ket x minus is 1 over square root of 2 column vector 1 minus 1, and bra x minus is 1 over square root of 2 row vector 1 minus 1. These two states, x plus and x minus, they're orthonormal. You should check that for yourself. Now the y direction, it also has polar angle pi over 2, but it has azimuthal angle pi over 2, not 0 as it was for x. And we can just go to our formula for general n and substitute in, and we get that ket of y plus is 1 over square root of 2 column vector 1i, bra form 1 over square root of 2 row vector 1 minus I. And ket of y minus is 1 over square root of 2 1 minus I. And bra y minus is row vector 1 over square root of 2 row vector 1i. These are orthonormal to one another as well. Now we already know the z direction, but let's prove that our formula for arbitrary n also works for z. So for the z direction, the polar angle is 0, the azimuthal angle is arbitrary. Here I chose the azimuthal angle phi to be pi just to be a convenient choice of arbitrary overall phase. So we get that z plus is the column vector 1, 0. Bra z plus is the row vector 1, 0. Ket z minus, with the choice of phi equals pi, we get the column vector 0, 1 and the bra row vector of 0, 1. Those two states are orthonormal and agree with our basis states, because plus and minus z were our basis state spatial directions. Now, these normalized state vectors, they're identical, subject to overall phase, which we can change as we like, to the normalized eigenvectors for the Pauli matrices that we covered in lecture D2 toward the end of the lecture. The spin 1/2 normalized state vectors, ket x plus and x minus, they correspond to the eigenvectors for Pauli matrix sigma 1. So we are going to associate direction x, sigma x, with Pauli matrix sigma 1. Spin 1/2 normalized state vectors y plus and y minus correspond to the eigenvectors for Pauli matrix sigma 2, so we associate sigma y with sigma 2. Spin 1/2 normalized state vectors z plus and z minus correspond to the eigenvectors for Pauli matrix sigma 3, so we associate sigma z with sigma 3. Beware, an overall phase of an eigenvector does not change its probabilities. It does not change any observable expectation values. It does not change orthogonal projectors, which we will be using in this lecture. Different books and classes are free to choose their own preferences for overall phase. So some book might use one of the following eigenvector representations, different from what we're using, but equivalent. So as long as they use it consistently, it's fine. So you will sometimes see different eigenvector representations. The physics is the same, the results are the same as long as it uses it consistently, but you cannot mix and match two sources that use different representations. So be careful when comparing different sources and remain consistent. So if you're using some book or course to check this lecture, beware it could have chosen different arbitrary overall phases for any of the eigenvectors. This is a possible time to take a break. Now the SG machine operators, we need to know how the output states of SG machines are determined by the input state. The only thing we've done in prior lectures is say, well, the beam splits equally. We need to know more than that. Each output port has an associated observable or Hermitian operator, Hermitian matrix. These operators are of a special type called a projector, based on the eigenvectors of the observable for that SG machine. Let's start with the SGZ machine. It has one input, two outputs, a plus output and a minus output. We already believe that whatever comes out, the plus output, it's going to be some number, complex number, times the state Z plus, and whatever comes out the minus port is going to be some complex number times the state Z minus. The spatial direction for the SGZ machine is the plus Z direction, and not surprisingly, we gave it that name because of it. The intrinsic spin angular momentum component observable SZ for the SGZ machine is SZ equals h bar over 2, because it's a spin 1/2 particle, times Pauli matrix sigma Z. All of our SG machines are designed for spin 1/2 particles for this lecture. So for this spin component, magnitude is always going to be h bar over 2. The normalized eigenvectors of SZ are subject to overall phase and in our basis. Z plus, column vector 1, 0, and Z minus, column vector 0, 1. And you can verify easily that if you use SZ to operate on Z plus, you will get the result plus h bar over 2 times Z plus. You can do that using the Pauli matrix sigma Z. And if you do SZ operating on Z minus, you will get minus h bar over 2 times Z minus. So sigma Z is the correct operator to give us spin component SZ in general, but we need to think a little harder to understand, to find an operator to tell us how we get a particular output state at an output port from an input state. So I tell you, and you can believe me, that the operator for the SGZ plus port is this projector, operator SGZ plus. It equals the projector of ket Z plus bra Z plus, which is to say, project the input onto Z plus, and that's how much the output gets of Z plus. Now the ket the ket form of Z plus is the column vector 1, 0. The representation of the bra form Z plus is the row vector 1, 0. This is a column vector times a row vector, a 2 by 1 by 1 by 2 multiplication, and we can do that, and we end up with a 2 by 2 matrix. The 2 by 2 matrix has 0 in all elements except the upper left 1, 1 element is 1. When we apply this operator to some state vector, input state vector V, the result tells us how much of state Z plus is in state V. The operator for the SGZ minus port is the projector ket Z minus, bra Z minus, column vector 0, 1, row vector 0, 1, which gives us the 2 by 2 matrix, which is 0 in all elements except element 2, 2, which has value 1. Now each of these operators is Hermitian. The main diagonal elements are real. The off-diagonal elements are complex conjugates of one another. They're 0 and complex conjugates of one another. Since the matrices are Hermitian, they are observables and will give real results. Now, you can and should verify that the sum of these two projectors is the identity matrix. The difference of these two projectors is the Pauli matrix sigma z. The effect of each projector is to determine how much of the input state projects to that output state. We are going to use these projectors and the X, Y, and Z representation of states in 9 Stern-Gerlach experiments to see how spin 1/2 states behave. This is a possible time to take a break. Now we can do the same thing for the SGX machine. Spatial direction is plus x, intrinsic spin angular momentum component observable is Sx, corresponding Pauli matrix sigma x, normalized eigenvectors of Sx are x plus and x minus. You can plug them in and check that they are the plus and minus eigenvalue, plus and minus h bar over 2 eigenvalues. The operator for the SGX port, XGX plus port, is this projector, ket x plus bra x plus, and it has this column vector form and this row vector form, and we can multiply them together, and we get the matrix 1/2 times 2 by 2 matrix with 1 in all 4 elements. The operator for the SGX minus port is the projector x minus, ket x minus, bra x minus. Same deal, different representation. Column vector form, row vector form, can multiply them together. We get this 2 by 2 matrix for its projector. If you add these two projectors together, you get the identity matrix. If you subtract them, you get Pauli matrix sigma x. Each of these operators is Hermitian, it's observable, they sum to the identity matrix, they difference to the Pauli matrix sigma x. The effect of each projector is to determine how much of the input state projects to that output state. SGY, same drill, different details. Direction is plus y. Intrinsic spin angular momentum observable. Component observable SY. Pauli matrix sigma y. Normalized eigenvectors, you can check that they are eigenvectors. You could check that they have the appropriate eigenvalues, a projector for the SGY plus port, cat Y plus, bra Y plus, column vector form, row vector form, multiply them together, we get a 2x2 matrix. You can easily see that the matrix is Hermitian. Do the same thing for SGY minus. We have ket Y minus, bra Y minus, column vector form, row vector form, multiply them together, we get a 2x2 matrix. It is Hermitian, it is observable. If we add the two projectors together, we get the identity matrix. If we subtract them, we get Pauli matrix sigma Y. Now, let's take a general direction in space. We'll take the direction n vector in space, and we'll call the machine an SG n vector machine. We have not covered this in a previous lecture. We're making it up here as we go. That's fine. We know how to do the operator for the projector for the plus port. It would be whatever ket n vector plus is times bra n vector plus. We already worked those out in an earlier step. So we have a column vector and a row vector. We multiply them together. We get this matrix. Looks a little involved. We can do the same thing for the n minus port. We already, so we have ket n minus bra n minus. We already worked out the column vector and row vector forms. We multiply them together. We get a matrix. If you look at both of these matrices, you can tell that they are Hermitian. You can sum them together and you will get the identity matrix. Now that we have these, you can plug in appropriate values for theta and phi and find that these exactly will give us the x, y, and z projector operators. You can do that. You probably should do that to be sure you understand. The effect of each projector is to determine how much of the input state projects to that output state. Now, leveraging the commutators of the Pauli matrices from lecture D2, we have that the intrinsic spin angular momentum component observables Sx, Xy, and Sc, they do not commute because the Pauli matrices do not commute. So they do not commute, and we have commutation relations as follows. The commutator of Sx with Sy is IH bar Sz, YZX, ZXY, order matters. Since the component observables do not commute, they do not share eigenvectors. Well, if you look back, you'll see that yeah, the eigenvectors for Sx were different than the eigenvectors for Sy, which were different than the eigenvectors for Sc. Now, this is going to be important to how spin states work and what measurements do. We'll see that later. Now, we can relate this to something you already might know. Possibly you know that rotations of objects in real space do not commute. If you do one rotation and then a second rotation, that's not generally the same, you don't get the same result as if you perform the rotations in opposite order. Start with some object where you can distinguish its orientation. Could be a cell phone, could be a book. Choose X, Y, and Z axes in space. Those axes will not move as you rotate the object. Those axes will be fixed. Start the object in some fixed orientation that you will remember, or write down what the orientation is. Rotate the object 90 degrees counterclockwise around the plus x-axis, and then 90 degrees counterclockwise around the plus y-axis. Remember this orientation of the object. Put the object back in its original orientation. Now rotate the object 90 degrees counterclockwise around the y-axis first, and then 90 degrees counterclockwise around the plus x-axis. The rotated orientation of the object is different now than after the first pair of rotations. Finite spatial rotations of objects are non-commutative. This relates to spin angular momentum, but not in a way that we're going to be able to prove out in this introductory series of lectures. But a real course in quantum mechanics will show you how that all works. Now, we want to use these SG machine output port projector operators to see and understand the results of actual experiments to confirm that our understanding of spin 1/2 spin states is correct. We're going to go through 9 examples of SG machines and see what our states and our projectors say the experimental result would be, and then I will tell you that actual experimental results agree with that. This is a possible time to take a break. Let's start with the oven and an SGZ machine. Originally, we had a Stern-Gerlach SGZ experiment using, we'll look at it with spin states and projector operators, which we didn't do in a prior lecture. So we'll use what we've developed in this lecture. But the setup is the same setup as we used in the D1 lecture. So the magnetic field will be oriented in the Z direction. The silver atoms will be traveling in the Y direction. They will come out of an oven. They'll have arbitrary magnetic dipole moment orientations coming out of the oven. The beam will split into 2 beams, a spin up or Z plus or Z up beam, and a spin down or Z minus or Z down direction. Neutral silver atoms came out of the oven with their spin states pointing in arbitrary directions in real space. Now, there's a problem with saying pointing. I will cover it later in this lecture, but there's not really a better wording for it. So I'm going to leave pointing in quotes, and we'll talk about that at the end of this lecture. So the spin state of a single silver atom whose spin state points in the direction n in space, n meaning polar angle theta with respect to the now fixed z-axis and azimuthal angle phi. So in a silver atom whose spin state points in the direction n vector in space has the following spin state entering into the input port of the SG machine. It's exactly what we covered earlier in this lecture. It's in state ket n plus, and so its state vector is cosine theta over 2 sine theta over 2 e to the I phi, where there's an arbitrary overall phase. We're going to feed that into an abstract SGZ machine, and we want to know what's the state going to be at the plus output port and what's the state going to be at the minus output port. To find the spin state of that atom, if it were detected exiting the SGZ plus output port, we operate on the input state with the operator SGZ plus, which we've previously worked out. So we know what the input port, what the state is going to be at the input port. The state is n vector plus. We want to know what the state will be at the Z plus output port, so we operate on this input state with operator SGZ plus, which we've previously worked out. We previously determined that operator SGZ plus is this matrix, 1, 0, 0, 0, and we previously worked out that vector, that spin state vector n vector plus is the column vector cosine theta over 2 sine theta over 2 e to the I phi. This is a 2 by 2 matrix times a 2 by 1 column vector. We can multiply them. It's easy to do. We get the result cosine theta over 2, 0. This is not normalized. Okay, we did not take steps to normalize it, nor do we want to. What we're going to do is we're going to pull the cosine theta over 2 out, and we get that the output port is going to have a state of cosine theta over 2 times z plus. Ket z plus is normalized, but when we multiply it by this factor, the output state is not normalized. Now, we can find the probability of the particle exiting that port. If and when we do a measurement or detection, it is norm squared of the output spin state. And that is cosine squared theta over 2. Going forward, we'll simply call this the probability of exiting the output state. I won't always remind you that it is norm squared of the state. We'll leave implicit that this is conditional on the experiment's inputs and that the state collapse only occurs when we finally do a measurement or detection. So we will just say, the probability is this. Now, to find the spin state of that atom if it were detected exiting the SGZ minus output port, we operate on the input state with the operator SGZ minus, which we've already worked out. So here's operator SGZ minus 0, 0, 0, 1. Here is state n vector plus cosine theta over 2 sine theta over 2 e to the I phi. We multiply them together. We get this state vector 0 sine theta over 2 e to the I phi. We can pull out sine theta over 2 e to the I phi times the ket z minus. We could take its probability, norm squared. When we do norm squared, the phase e to the I phi cancels, does not contribute. We get probability sine squared theta over 2. Now, note that the sum of the probabilities of exiting the plus and minus ports equals 1. We get cosine squared theta over 2 plus sine squared theta over 2. Trigonometry tells us that that is always 1 regardless of the angle theta. So the probability of it exiting one of the two ports, some port, is 1. The particle did not get lost, it did not get absorbed, it did not get destroyed. Each particle that enters the input exits one of the outputs once a measurement or detection is done. Neutral silver atoms came out of the oven with their spin states pointing in arbitrary random directions in real space. So let's average the probabilities across all angles of space, equal probability for every angle. We get that the average probability of exiting the plus port is 1/2, and the average probability for exiting the minus port is 1/2. This matches the Stern-Gerlach experiment, which determined only qualitatively that the beam of silver atoms accumulated equally on the two spots. But if we were to actually use detectors instead of, silver atoms accumulating on a glass plate, if we were to use electronic detectors and run 1,000,000 atoms through the experiment, we would find that we get about 1/2 detected at the plus port and 1/2 detected at the minus port. Not exactly 1/2. There will be statistical fluctuations, but the more atoms we feed through and detect, the closer the probability, the experimentally measured probability will get to a number of 1/2. So from now on, we're going to ignore the oven, and instead of starting with an arbitrary direction, we're going to start with a single atom that has exited the SGZ plus port and is in normalized spin state Z plus. So we're going to feed Z plus, a single Z plus atom into 8 more experiments and see what the results are. This is a possible time to take a break. Experiment 2, we're going to feed Z plus as input to an SGZ machine. Now you might say you already know the answer, what it must be, and if you do, great, assuming you're correct. Let's use the normalized Z plus state as input to an SGZ machine. Easy enough. To find the spin state of the particle, if it were detected exiting the SGZ plus output port, we operate on the input state. Now the input state is Z plus, so column vector 1, 0. We operate on that with the operator, projector operator, SGZ plus. We've already calculated that. We calculated that as 1, 0, 0, 0. We can do this multiplication. We end up with the column vector 1, 0, which is just the Z plus ket. Its norm squared is 1. Its probability is 1 to find the spin state of the particle. If it were detected exiting the SGZ minus output port, we operate on the input state with the operator for SGZ minus. We already know that operator, it's 0, 0, 0, 1. We operate on it. We get 0, the 0 state, and its norm squared is 0. So if we start with Z plus and we feed it into an SGZ machine, every atom that we feed in comes out the Z plus output port, and none come out the Z minus output port. This all makes sense. It's what we would expect. It might be what you expected. We know that Z plus and Z minus states, they're physically orthogonal. They have 0 overlap. We use that as a condition to getting started in this lecture. We could add as many additional SGZ plus machines as we want, one after the other, and we would always get the same result. So now we've done 2 experiments. Now we're going to do a third, and this one will be less obvious. This is a possible time to take a break. Let's use the normalized Z plus state as input to an SGX machine. Our procedure is the same as always. We know the input state, column vector 1, 0. We need the operator for SGX plus, so we go back and look at our previous operator, and we had the operator 1/2 times 1, 1, 1, 1. Matrix times a column vector. We know how to do that multiplication. We multiply it out. We get 1/2 times column vector 1, 1. If we think about it, this is 1 over square root of 2 times the normalized vector x plus. And the probability, the norm squared of that, is 1/2. We can calculate the probability 2 ways. We can do norm squared of the final state, and we get 1/2. Alternatively, we can do the inner product of the vector with itself, and here we have the column vector form, and we could turn it into the row vector form. So 1/2 row vector 1, 1 times 1/2 column vector 1, 1. You can multiply this out, and you'll get 1/4 times 1 plus 1, or 1/2. To find the spin state of the particle if it were detected exiting the SGX minus output port, same procedure, different operator. Column vector 1, 0, the operator for SGX minus. Multiply them together, we get a column vector. And if we think about it, we can restate that as 1 over square root of 2 times ket x minus. And the probability of that output state is 1/2. So if we feed the normalized Z plus state as input to an SGX machine, we get equal probabilities of 1/2 of exiting the plus or minus output states. And this is what the experimental results would show. If you used actual detectors, that's what you would get. The X and Z axes in space are orthogonal, but the Z plus and X plus spin 1/2 states, they are not physically orthogonal. They have some overlap. They're not independent. So this spin system is definitely not classical. Classically, an object with angular momentum solely along the z-axis has no component of angular momentum along the x-axis. They're orthogonal directions in real space, and so classically the angular momentums would be orthogonal, but not for the quantum mechanical spin state space. Now you might say, well, but how does the Z plus state turn into the X plus and X minus states? Aren't they separate states? They look separate. I mean, we're writing them separate. Aren't they separate? And no, they're not separate. This is a two-state system, a two-dimensional abstract vector space. We can characterize it by any two non-zero orthogonal spin 1/2 state vectors as basis vectors for the representation of the entire vector space, but two vectors that are not orthogonal are not independent of one another. So you can express them in terms of the basis vectors. The state X plus is a specific linear combination of Z plus and Z minus. So no, they're not separate. They look like we write them differently, but they can't be separate. It's only a two-dimensional space. So they look like they're written separately, but they are not independent. They are not physically orthogonal. And that's how you can feed in Z plus and get out X plus. There is a more complicated, subtle issue here, though. Our SG machines measure the component of intrinsic spin angular momentum in the direction of that machine. Does that mean the spin angular momentum was pointing in that direction? Is there something else about spin angular momentum besides these quantized components? We will cover this in a later section of this lecture. And if you get tired of this lecture, if you get tired of the endless experiments showing how spin 1/2 works, don't quit the lecture. Skip ahead to the end and get this extra material. Now, we would have gotten comparable understanding and equal probability, but maybe different overall phase, if we had fed, instead of feeding in Z plus, we fed in Z minus as input to the SGX machines. You would still have gotten equal probability for X plus and X minus, the two outputs, and maybe you would like to verify this for yourself. This is a possible time to take a break. Experiment 4. Let's feed Z plus as input to an SGY machine. Now, you can ask yourself, without doing the math, what do you expect the results to be? And you could say, well, saying y versus x, that's just a label. We should probably get equal probability of coming out the y plus port and the y minus port. I mean, why would it be different? Let's see. Same procedure. We know the input state, z plus or column vector 1, 0. We need to apply the output projector, SGY plus. We already calculated that. It's this matrix. Matrix times a column vector. We multiply it. That's not hard to do. We do that. And then we think about it and we figure out that the actual output is 1 over square root of 2 times y plus. Calculate the probability. The probability is 1/2. Do the same thing for y minus. Probability 1/2. So this is what we might reasonably expect the result to be. Same probability result as using the SGX machine. Here we use the SGY machine. Isn't spin 1/2 an interesting, odd system? Let's do some more experiments. So the normalized z plus state as input to SGY machine gives equal probabilities of 1/2 of exiting the plus or minus output ports. That is what the experiment would show if we had actual electronic detectors. The y and z axes in space are orthogonal, but the z plus and y plus spin 1/2 states are not physically orthogonal. They have a specific overlap. They are not independent. This is a possible time to take a break. Experiment 5. Let's use the normalized z plus state as input to an SGN vector machine. We already calculated those projectors. Now this is an exercise for you to do. I'm not going to do it. Determine the spin state of the particle if it were detected exiting the SGN plus output port. Then determine its probability. Likewise for the state for the N minus output port. Figure out its probability. Assure yourself that the probabilities sum to 1. And then use different angles to show that from this SGN machine, you can get the prior SGZ, SGX, and SGY results from the SGN results. If you want to check this for yourself, I encourage you to do it. You'll be happy that you understand how to do the math. You will be more confident that you understand states. You will be more confident that you understand projectors and probability. So I encourage you to pause the video now and do this work for yourself. I don't have a way of grading you, but I encourage you to do that. This is a possible time to take a break. Experiment 6. Let's use the normalized z plus state as input to an SGX machine, and then we'll follow that. We'll take the result of the SGX plus output port, which is going to be spin state 1 over square root of 2x plus. We already calculated that. We're going to feed that as input to an SGZ machine, and we're going to see what its two outputs are. So we start with Z plus, we feed it into SGX, we're going to ignore the minus output, we're going to take the plus output, which we already know the state. The state is 1 over square root of 2x plus, we know that already, so we're not going to recompute that. We're going to feed that into an SGZ machine and see what are the plus and minus outputs. Same procedure as always, it's just now We're interested in this second box, the SGZ box, and its input is 1 over square root of 2 x plus. So we already know that that is 1/2 times the column vector 1, 1. And we know the operator for SGZ plus, it's this matrix 1, 0, 0, 0. We know how to multiply them together. We get 1/2 times the column vector 1, 0. That's 1/2 times ket z plus. And the probability is norm squared of that, which is 1/4. We can do the same thing for the Z minus output port. I encourage you to do that. We get 1/2 Z minus. Its probability is 1/4. Now we have to say, oh, where did that probability go? So for a single particle input to the SGX machine, it started out as normalized. It was a definite particle. There was probability 1/2 of exiting the X plus output port, probability 1/2 of exiting the X minus port, but we're ignoring all the particles that exited the X minus port. We're letting them all fall on the floor. So if the particle did exit the SGX plus output port and would enter the SGZ input port, its probability then splits equally between SGZ plus and SGZ minus. So total probability 1/2 of exiting the X minus port and we throwing it away, and then 1/4 of exiting the SGZ plus output port and 1/4 of exiting the SGZ minus output port. Total probability is 1, but the probability is only 1/2 of coming out of the SGZ machine because only 1/2 of the particles entered it. And that is what experimental results would give. Now, but this is weird. Why? We started out with a particle in the Z plus state. We fed it into a box. We fed it into another box, and then we got some finite probability of it being in the Z minus state. We got probability 1/4 that it would come out in the Z minus state. The overall experiment, we started with a Z plus, and we know that Z plus and Z minus are physically orthogonal. We fed it into this box, fed it into this box, and we got out some Z minus. Whoa, this is telling us something about physical reality and spin states. Why is there any probability for SGZ minus when the original particle was in spin state Z plus? Doesn't the experiment remember that original spin state? No. The experiment does not remember the original spin state in this case and in general. The intrinsic spin angular momentum component observables, Sx, Xy, and Sz, they don't commute, so they don't share eigenvectors. We showed that they don't commute in lecture D2. We showed that the Pauli matrices do not compute. So these observables do not share eigenvectors. An eigenvector of one of these observables is not an eigenvector of the other two observables. Therefore, if we operate on an eigenstate of one spin operator with another spin operator of a different direction, we inescapably alter the state. And this inescapably means that we add in some of the orthogonal eigenstate that had zero amplitude in the original state. Therefore, the original state does not get remembered. The original state affects the final state, but the last operation performed alters any state that is not one of its eigenstates. Now, you might hear something to the effect that the final quantum mechanical operation gets remembered and earlier operations get forgotten. That's not really precise, but it is memorable and it is useful. So we must not think that there is a state that is simultaneously z plus and x plus, or simultaneously sz equals plus h bar over 2 and sx equals plus h bar over 2. There is no such state. These are not independent sequential filters. However, as we showed, there is a state of operating on z plus with operator sg x plus. Probability amplitudes of state vectors and probabilities does not mean lack of knowledge of the state on our part, and superposition does not mean that the system is splitting its time between states according to probabilities. The state vector tells us completely the state of the system, but it is a probability amplitude and has a probability. We could have gotten comparable understanding and equal probabilities, but different states, if we had fed the SGX machine's SGX minus output port spin state as input to the SGZ machine, or if we had used an SGY machine in place of the SGX machine. Perhaps you'd like to verify this for yourself. This is a possible time to take a break. Experiment 7. Let's use the normalized Z plus state as input to an SGX machine, and the SGX machine's SGX plus output port spin state, which we already know is 1 over square root of 2 x plus. Let's use that as input to an SGY machine. Our procedure is the same. We know the input port. Now here the input, it's the input state to the SGY machine. 1 over square root of 2 x plus, which we know in column vector form is the same as 1/2 1 1. We know the operator for SGY plus. You just have to go back and verify that this is it. Matrix times column vector, you can multiply that out. This one's a little more complicated because it does have complex numbers in it. We can pull out a factor of 1 minus I from the first component, and then the second component just becomes I. You know, I times 1 is I times minus I is plus 1, so that works out fine. And so with a little work, we get the ket y plus with an amplitude 1 minus I over 2 square root of 2. Its probability is norm squared. You should be able to do that. Its probability will be 1/4. If you want, you can take the output state, and you could calculate its probability as the inner product of itself with itself. Should give you the same results. We can do the calculation for the SGY minus output port. We have its operator matrix. Calculate it out, do some math, probability of 1/4. So for a single particle input to the SGX machine, there was a probability of 1/2 of exiting the SGX plus output port. Probability of 1/2 of exiting the SGX minus output port. If the particle did exit the SGX plus output port, it would enter the SGY input port, and its probability then splits equally between SGY plus and SGY minus output ports. And that's what experimental results would give. This is a possible time to take a break. Experiment 8, something from nothing. This is a 2-part experiment. First, we confirm that there is zero overlap, zero inner product between Z plus and Z minus, which we already know, but let's confirm it. We give Z plus as input to an SGZ machine and we measure the minus port. We get zero amplitude, zero probability, no particle, no surprise there. If this is not obvious to you, you should do it. Now we're going to insert an SGX machine in here between the Z plus input state and the input state of the SGZ machine. And we'll send the plus output of the SGX machine to the input port of the SGZ machine. We're going to discard the minus output of the SGX machine. And we're going to be interested in the minus output port of the SGZ machine. Now, we've already solved this case. The SGZ minus output, it's going to have amplitude 1/2 and probability 1/4, not 0. So with nothing in the middle, we get 0 probability for a Z minus output. But when we insert a box in the middle, we get non-zero probability for Z minus. In a sense, we get something from nothing by inserting the SGX machine and discarding its minus output. This can seem mysterious, and you might even think it's wrong, but it actually follows simply from the math of quantum mechanical state vectors, operators, and probability. It's an aspect of two-state systems. We can only have, two basis states. And so when we start to do experiments like this, we get some component that we naively might not expect. We would naively expect this to be 0 if we were wrongly thinking of, well, this is Z plus and X plus. Well, it's not. It's a two-state system. It only has two basis vectors, and so we can't think of it that way. Now, if this feels like cheating, or you think it cannot be true, this is actually an experiment that you can perform yourself, the equivalent with light, and it's very inexpensive. You need 3 linear plane polarizers. These can be very inexpensive, small plastic polarizer sheets. Look at some medium bright artificial light source, but not the sun. Orient one polarizer vertically and look through it. The light is now a little less intense. Orient a second polarizer horizontally and look through both of them in series. Now, little or no light gets through the pair. If they were perfect polarizers, no light should get through and it should be, jet black. But real polarizers are not perfect and you're not holding them perfectly perpendicular. And so some light gets through, but it should be dark. Now, take the third polarizer, orient it at 45 degrees, insert it in between the first two polarizers. Some of the light gets restored. We restored something from nothing. This would be what the setup would look like. The polarizer behind is a vertical polarizer. The polarizer in front is rotated to be horizontal. This polarizer is rotated to be 45 degrees. When we look at light through these two, it should be dark, but then as we slide this polarizer in, some light gets restored. Now, You could say, well, this is just a classical electromagnetic wave experiment. I know that happens from electromagnetics. No big deal here, nothing going on here. And that's true, it's a classical experiment. But why does it work that way? It works that way because light consists of photons. Photons are spin 1 particles, which we have not discussed yet. Orthogonal physical states for spin 1 particles have 90 degrees between them in real space, unlike 180 degrees of spin 1/2 particles. So it's an equivalent related experiment. The angles are different, but it's a related experiment to show that you do get something from nothing, and it's because these are 2-state systems, 2 basis vectors. This is a possible time to take a break. Now we're on our 9th and final experiment. I'm sure we're all sick to death of these Stern-Gerlach experiments by now. This will be the final one, and then we'll cover some new material. Here we're going to use a modified SGX machine. Recall that we defined that in the prior in lecture D1, I think. So let's use the normalized Z plus state as input to a modified SGX machine. Now the modified SGX machine has only 1 output port. It has the ability for us to block 2 internal paths, a plus path and a minus path. But we're not going to block those paths here. So our expectation is that this modified SGX box should do nothing. If we feed in Z plus, we get out Z plus. Except we know how it works internally. Internally, there's an SGX plus path and an SGX minus path. So let's find the spin state of the particle in the plus path. We take the input state, SG Z plus, column vector 1, 0. We operate on it with projector SGX plus. This is the projector. Operate on it. We get that in that state, the plus path, the state is actually 1 over square root of 2x plus. To find the spin state in the minus path, we operate on the same input state, but with the projector operator SGX minus. And in the minus path, the state is 1 over square root of 2x minus. Now, if we blocked either path from the output, from the outside of the device, we would get, if we block the minus path, the output state would be 1 over square root of 2x plus. If instead we block the plus path, the output state would be 1 over square root of 2x minus. But what if we don't block either path? If we block neither path, the output state vector is the sum of the state vectors in the plus path and the state vector in the minus path. We already calculated what the state vectors are in those paths. Now we just need to add them together. 1 over square root of 2x plus 1 over square root of 2x minus. Well, we know from before that that's 1 over 2 column vector 1, 1 plus 1 over 2 column vector 1 minus 1. And if we add those together, we get column vector 1, 0, which we know is the Z plus state. So we use the projectors to tell us what's happening on the paths, and because we were not blocking either paths, we then added the state vectors together. And in the end, this modified SGX machine did nothing. It preserved the input state to the output state. It's a modified SGX machine, but it preserved the Z plus state from the input to the output. No probabilities anymore. We know 100% the output state is Z plus. There's no probability to be found here other than probability 1. We got that result because we blocked neither internal path, and more subtly, because we made no attempt to measure or determine which path the particle took inside the machine. That subtlety is important. Since we made no attempt to measure which path, the output state vector is the sum of the path state vectors, not a measured collapse state. If we had made any attempt to determine which path the particle took, even if we did not look at the result, we would have altered and collapsed the result. In such a case, the output would not have been Z plus. I believe the output would have been either X plus or X minus, each with a probability of 1/2. So when we make no attempt to measure or determine which path the particle took, which path did the particle take? Now, we've discussed this in 2 lectures before. B6, the double slit experiment, and B7, the Mach-Zehnder interferometer experiment. When a particle can or could take multiple paths or trajectories within a system or experiment, the particle's wave function or state vector is a superposition or linear combination of the wave functions or state vectors that would obtain for each possible path. This is when we don't try to look at which path. It's wrong to say that the particle took both paths. It would be better to say that the wave function or state vector is as if the particle could take either path, and we don't know which path it did take. If we didn't measure which path was taken, plus path, minus path, or both paths, then we simply don't know which path, and that's the end of the story. We should not make any guess about it. We should not try to apply human, macroscopic world experience, reason, or logic to a quantum world measurable quantity that we did not measure. All experiments verify this. This is true even if we add instrumentation measurement, but we do not look at the result of which paths get traversed. Just adding the mechanism to either path changes the system and the results. Suppose that instead of treating the 2 paths within the modified SGX machine as quantum mechanical states, we had treated them only as probabilities. This would have predicted that the output would have been X plus with probability 1/2 and X minus with probability 1/2. It would not have predicted that the output would be Z plus. It's wrong to view the 2 internal paths as merely probabilities instead of quantum states when we make no attempt to measure or detect which path gets taken within the machine. Summing the quantum states of the 2 paths within the modified SGX machine gives us an interference, just as we had in the double slit experiment of lecture B6 and the Mach-Zehnder interferometer of lecture B7. When we don't make a measurement of which path, we must add the states of each path, which other books or courses may call adding the amplitudes or the probability amplitudes. We must not add the probabilities. If we did measure or detect which path, then we've altered the states and we must add the probabilities. Quantum mechanical reality is mysterious, but the physics and mathematics of quantum mechanics tells us how the system behaves. This is a possible time to take a break. S squared, angular momentum squared. This section is optional and it is at least a little confusing. If it's too confusing, skip it and ignore it and you'll be fine. However, for some learners, this section will help understanding even though it is mysterious. For the entirety of this lecture, we've talked about the component of intrinsic spin angular momentum in some direction in which we make a measurement. That component in that direction is the quantized quantity, so it's important to understand it. But it's not the entire picture. When we found that a particular spin 1/2 particle's spin component was z plus, you might have imagined consciously or subconsciously, or my wording might have suggested that its x and y components of spin were therefore 0, and that its spin angular momentum definitely points in the z plus direction. This is not correct. At that point, its x and y components of spin are unmeasured and uncertain because simultaneously measuring angular momentum in different directions is incompatible. Those operators do not commute. Let's see what happens starting with squaring the spin component operators. Sx is h bar over 2 times the Pauli matrix sigma x. We can square it. We get h bar squared over 4 times the Pauli matrix sigma x squared. But each Pauli matrix, when we square it, gives the identity matrix. Each of the Pauli matrices squares to the identity matrix, as we've seen in the last lecture, D2. So Sx squared equals Sy squared equals Se squared equals h bar squared over 4 times the identity matrix. Now we're going to define S squared, the intrinsic spin angular momentum squared, not a component anymore, total angular momentum, total spin angular momentum squared. We're going to define that as Sx squared plus Sy squared plus Se squared because they're orthogonal directions in space, Cartesian axes. And when we add them together, we just get 3 copies of this, so we get 3/4 h bar squared times the identity matrix. Since S squared is proportional to the identity matrix, which commutes with any other matrix, the S squared observable commutes with any one of Sx, Sy, and Se, and eigenvectors for those spin component operators are also eigenvectors for S squared. We could always measure S squared along with Sx, Sy, or Se if we need to determine the intrinsic spin angular momentum magnitude of some particle. However, there's no need to measure S squared if we know definitely that the particle has spin 1/2. For a spin 1/2 particle, we say that spin lowercase s equals 1/2 and that S squared equals S times S plus 1 h bar squared identity. And with S being 1/2, we get 1/2 times 3/2, we get 3/4 h bar squared times the identity matrix. So if we didn't know the spin of a particle, we could measure S squared and the measurement would give us some quantized result, and from that we could find the spin value S. But for this lecture, we know it's spin 1/2. From this, we can imagine a new intrinsic spin angular momentum vector, S vector, in real three-dimensional space. So it's a vector in three-dimensional space pointing in some direction in real space with dimensions of angular momentum, but each of its components is then a quantum mechanical operator. So this is confusing. The vector, S vector, has a length of square root of 3 over 2 h bar for spin 1/2. So the tip of the spatial vector lies on the surface of an angular momentum sphere of radius square root of 3 over 2 h bar. So let's look at this for a spin 1/2 particle whose spin component has been measured in the z direction. This blue is the spin 1/2 sphere, but we're only looking at the xz plane, so it looks like a circle in this plane. It has radius square root of 3 over 2 h bar. Horizontal is the x direction, vertical is the z direction. We're measuring this spin 1/2 particle's z components of spin, and that measurement will be quantized. We either will get a z component of plus h bar over 2 or a z component of minus h bar over 2. No other measurements are possible. That is what happens in a spin 1/2 system. When we measure S sub z, we get quantized plus or minus h bar over 2, but when we measure S sub z, S sub x and S sub y are indeterminate. If we measure S sub z and got h bar plus h bar over 2, that would be this green horizontal bar. But it's not actually a bar. We're just showing this in a plane. What it really is the intersection of the plane z equals h bar over 2 with the blue sphere. So it's a green circle in the plane perpendicular to the plane we're looking at. And while SZ has a definite value, plus h bar over 2, on that circle, Sx and Sy the spin vector can point anywhere along that circle, and we don't know where it is pointing because we are not measuring that. We've measured Sz, we're not measuring Sx and Sy. So Sx and Sy could have any value along that circle. Likewise, if we measure Sz and we get the value minus h bar over 2, then Sx and Sy are anywhere along the red circle, which in the plane looks like a red line segment. So these line segments are actually circles. The circles have radius h bar square root of 2 over 2 in the perpendicular plane. Now, let's look at this for a spin 1/2 particle whose spin component has been measured in the x direction. The blue sphere is the same, but now this should say x components, not z components. The plus x component of spin is plus h bar over 2 here, and this represents a circle in the perpendicular plane, and the minus x component has spin minus h bar over 2. This is a possible time to take a break. Switching gears, we have talked about operators, but the operators in this lecture have all been projection operators so that we could find the probability of exiting an output port of an SG machine. Here we're going to switch, and the operator is going to be the Hamiltonian. We're not going to do the operator, but we've switched for the operator to be the Hamiltonian so that we get energy levels. Electron spin and atomic orbitals energy levels. The atomic orbital energy levels for hydrogen atom and other atoms, they get shifted and or split by the magnetic interaction between the magnetic dipole moment of any unpaired bound electron and any of the following: an external magnetic field. This is called the Zeeman effect. We're not going to cover what that does to the energy levels, or the interaction between the electron and the magnetic dipole moment of that electron's orbital angular momentum in a p, d, or f orbital. This is called spin-orbit coupling, and it's part of the fine structure of the orbital energy levels. These energy corrections are generally less than 1/10,000th of the ground state energy, and so those energy transitions are in the infrared range, not the visible or ultraviolet light range. The magnetic dipole moment of the electron can interact with the magnetic dipole moment of a proton or a neutron in the nucleus. This is called hyperfine structure and is generally less than 1/1,000,000th of the ground state energy level. Energy transitions are in the microwave range. These effects, they're easily seen in spectroscopy. They're important to chemistry. They're important to astronomy. We're not going to study the effects. I just wanted to make you aware of them, that they all stem from the magnetic dipole moment of the spin, the intrinsic spin angular momentum of an unpaired electron in an atom. This is a possible time to take a break. Now, we're almost done with the lecture. Let's step back and do a summary takeaways for spin 1/2 particles and their spin states. Last lecture we did two-state systems and we got a bunch of properties. Spin 1/2 particles inherit all those properties that we covered in lecture D2 and add the following specific characteristics of spin 1/2 particles and their spin states, which is probably the most important instance of a two-state system, but not the only instance. For spin 1/2 particles, whether they're electrons, quarks, neutrinos, protons, neutrons, the two independent non-overlapping physical basis states, basis vectors, for spin 1/2 are a unit vector pointing in any direction in real three-dimensional space and the unit vector pointing in the opposite antiparallel direction. This 180-degree spatial angle between the two physical basis states is dictated by the quantum physics of all spin 1/2 spin states, not dictated by simply being a two-state system. In this lecture, we called these directions plus z and minus z, as is customary, which is convenient for then using physical coordinates, which is why we do it. but we could have chosen any direction and we could have given it any designation. We can remember the 180-degree constraint on the basis vectors by remembering that the beam of silver atoms splits into two beams based on whether the unpaired electron's component of intrinsic spin angular momentum and magnetic dipole moment is parallel to or antiparallel to the direction of the magnetic field. For spin 1/2 states, there's a 1-to-1 correspondence between any normalized state vector in the two-dimensional abstract state vector space and a unique direction in real three-dimensional space. For a spin 1/2 particle with spin state component, positive eigenvalues, eigenvector direction, vector n in real physical space, so spherical coordinate, polar angle theta, and azimuthal angle phi, that spin state's normalized state vector in the abstract state vector space, representation in our basis, subject to arbitrary overall phase, is n plus is cosine theta over 2, sine theta over 2 e to the I phi. So from the general two-state system, we map alpha to physical angle theta over 2 and beta to physical angle phi. However, you must not think of the abstract vector space as being physical space. With our spin 1/2 basis vectors being z plus and z minus, we can associate two-state system Pauli matrices sigma 1, 2, and 3 with spatial directions x, y, and z. Sigma x is sigma 1, sigma y is sigma 2, sigma z is sigma 3. For an SG machine, we have identified the operators that operate on an input state to give an output state as orthogonal projectors. For the SGZ machine plus output port, the projector is ket Z plus, bra Z plus, which is a 2x2 matrix, a 2x2 Hermitian matrix, and so an observable. The intrinsic spin angular momentum component observables Sx, Sy, and Se do not commute. They do not share eigenvectors, and they do alter one another's states. We have the following commutator relation for the spin angular momentum component observables. This is a possible time to take a break. Other courses. Our operators were 2x2 square matrices. Some books or courses use the term matrix mechanics for quantum mechanics of finite dimensional systems. However, the original matrix mechanics of Heisenberg, Born, and Jordan actually used infinite dimensional matrices to solve atomic energy levels. So there's a discrepancy in the words matrix mechanics that you should be aware of. If you would like a more visual depiction of spin experiments, I recommend the edX course Quantum Mechanics for Everyone at this URL. This course includes very nice simulated experiments with different Stern-Gerlach machines where you run the experiments and you look at the results so that you come to understand how spin works. And then after you're done with all your SG machine experiments, it continues with some interesting and mysterious aspects of quantum mechanics that we will not cover in this introduction. Now, if you followed all the material of this lecture and you would like to look at a quantum mechanics book, I suggest you look at John S. Townsend's A Modern Approach to Quantum Mechanics, 2nd edition. You'll be able to follow the first couple chapters if you could follow all the material of this lecture. Now, if you want more advanced material and you'd like to read the MIT OpenCourseware 805 lecture notes on spin 1/2 systems, those lecture notes are at the following link, but they use some material that we have not covered. This is the end of lecture D3.